So our next topic is the second derivative test for local extrema. As you saw in the previous section, we saw the first derivative test that we can use to determine whether a particular critical point is a min, a max, or neither. So we now have the second derivative test, which at least can tell us in some cases whether something is a min or a max. Let's suppose that x equals c is a critical point of f. If it is, then if f double prime of c, the second derivative of f evaluated at c, is positive, then x equals c is the location of a local min. And if f double prime of c is a negative, then x equals c is the location of a local max. By the way, notice that those don't seem to go together. It seems like if I'm looking for greater than 0, I'd be identifying a max, and if I'm looking for less than 0, I'd be identifying a min, but it doesn't work that way. As usual, I'm going to put up the picture, and hopefully it'll make a little bit more sense. The other thing to note is that if f double prime of c equals 0 or does not exist, then the second derivative test is inconclusive, and in order to classify the point as a min or a max or neither, you would have to use a different test. By the way, inconclusive doesn't mean that it's neither. It means we really, really don't know, and I'm going to put up some examples to show you just how much we actually don't know if you get a result of 0 or does not exist. By the way, one thing that's worth noting is that before I move on, one thing that's worth noting is that f of c, sorry, or rather I should say x equals c, has to be identified as critical because f prime of c equals 0, not because f prime of c does not exist. I'm not saying that if f prime of c doesn't exist, that c is not a critical point. It is. We saw what the definition of critical points is. What I mean is, for the purpose of this test is not useful unless we've identified c as being a critical point, because f prime of c is 0. Why is that? Well, if f prime of c doesn't exist, then neither does f double prime of c, so we'd never be able to use this test anyway. In some cases, f prime of c exists, but f double prime doesn't, and that's why I've written the third bullet point the way I have. But at the bare minimum, f prime of c has to exist in order to be able to even talk about what the second derivative is at c. So, not only does x equals c have to be a critical point, but we have to have identified it specifically in this way in order for this test to apply. So, let me just put up the picture and show you what we're talking about. Why does the positive or negativeness of f double prime affect whether a particular critical point is a min or a max? I've put in here two critical points, C1 and C2. We can easily see that these are both the type of critical point that's identified because the derivative exists but is equal to 0. So we have these horizontal tangents. Now, look what's going on here. For C1 is clearly sitting atop a concave down function. This is the telltale sign of a critical point being a max, is that it's sitting on top of a function that's concave down. On the other hand, for C2, it's sitting at the bottom of a concave up function. And this is the telltale sign of a point being a min, is that it's sitting at the bottom of a concave up curve. So this is why we have this definition that sort of looks like it would be backwards. We say that if f double prime is positive, in other words, if the function is concave up, then we found is concave up at c, then we found a min, and if it's concave down at c, in other words, if its second derivative is negative, then we found a local max. Hopefully, the picture here makes that conclusion make some sense.